Welcome to the fourth video in Introduction to Quantum Field Theory. In this video, we'll talk a little bit about the formalism used for spinors in quantum field theory. No proofs, more broad concept. The next video will be on spinor fields, which we'll use all of the information in this video, which talks about spinors. So in the traditional QFT formalism, what separates spinors from other quantities is how they transform. So spinors transform differently from vectors and scalars, or I'll say from scalars and vectors, which this is one of the reasons why I prefer geometric algebra, because, that's not true. Everything transforms the same way. But first off, scalars don't transform. And secondly, vectors, not possessive, vectors transform using 4x4 matrices. And then specifically, or you have spinors, so spinors, Weyl spinors, transform using 2x2 matrices. There exist left and right-handed versions. So not only are there, not only do they transform under 2x2 matrices instead of 4x4, but they also have left and right-handed versions. In geometric algebra, of course, vectors and spinors transform the same way, or specific classical spinors will transform using the same way vectors do, but also but then if you make an algebraic spinor, it transforms. You can derive the way that the spinor transforms from the way that the vector transforms, essentially from. So I'll give a little box in here. Talk about cool part of geometric algebra. You can have like everything. So like if you have some element in your geometric algebra, then the way it transforms is pretty simple. It maps to, so some element maps to a general rotor G R, and then I'm going to denote the reverse here with the Hermitian conjugate. So yeah, like every object in geometric algebra transforms like this. And so like if this is a vector, or do this, if this is a vector, then it's the same. If this is a spinor, then it turns out that the spinor is actually it basically is the spinor. So, and the way R would transform technically is because R is still an element of this algebra, so it would transform technically the same way. But if you're considering just the fact that you can compose So you can, if you can do this, can compose, and the fact that composition looks like this, it's the fact that composition looks like this, that it looks like it's one-sided. It'll be like it'll look like it's one-sided here because R1, R1 and these contain the same information. This contains the same information as that. So technically, R1 is being transformed by R2, which then transforms this object. So you can look at R2 as acting on R1, and if you consider R1 as the spinner, then you can consider R2 as acting on the spinner. But it shows that like these are all actually very interrelated, whereas here they look completely different from each other. So we'll denote right-handed. We'll denote right, or I'll do this, left-handed and right-handed vial spinners as eta and eta slash, respectively. And typically they use, these typically use A, B, C, and so forth for indices. So for rotations, left and right-handed vial spinners, because they transform under 2x2 matrices, that means that a single vial spinner, like a left or a right-handed vial spinner, has two components. And so and that's why they transform under 2x2 matrices. But general, left and right-handed vial spinners transform, or I'll say rotate, using the same matrix, or in geometric algebra terms, they use the same rotor. So you'll have that this maps to some rotor or matrix rotation matrix. You have your indices, and if you're a little confused about the indices, the next video will cover that. But just for now, treat them like the indices for other things that you've seen in the past videos. And slash or R A B is equal to cosine theta over 2 I sine theta over 2 I sine theta over 2 cosine theta over 2. And if you're interested, the geometric algebra equivalent, so in GA, it's just a rotor, which is equal to cosine theta over 2 plus sigma yz. So this is a bivector in the yz direction. Sine theta over 2. And this would just be e to the theta over 2 sigma yz. So you can see in geometric algebra, it's a very simple, it's just an exponential of a bivector, but here it's a matrix. But, so however, these spinors transform differently, or I will say they boost differently. So they have different matrices that represent the boost. So do this, and then I'm just going to follow the same format as here. Instead of a rotation matrix, you get a boost matrix, and there will be a geometric algebra equivalent. Oh, copy. Oops. Okay, so where the boost matrix looks like this: 0, 0, e to the phi over 2, and then e to the negative phi over 2. And then in geometric algebra, this would just correspond to, or I am writing these correspondences using the algebra of physical space, which is 3-dimensional. And this would be sigma z. This right here. Yes. This would be how it transforms. And then there is a corresponding right hand. So just to make things clear, and put left up here. And these are right-handed. And all it does is it negates the signs in these exponentials, which corresponds in geometric algebra to a negation of this basis vector. So in for spinors, they boost differently. And this would or this has a very elegant description in geometric algebra. So in 3D, I'm just going to explain it in 3D geometric algebra, also known as the algebra of physical space, or APS for short. There exist, or there's something called grade involution. There's grade involution. And that is if you have some object in the algebra, then there's something called grade involution, which I write with this little with the superscript minus, and it just flips the sign of all odd all odd k vector components. So there is something, but in quantum mechanics, there um there's parity, and in parity, that you have some vector x, which is these are only spatial components, and you take that and map it to negative x. And what this looks like is having a basis set like this, having your x, y, and your z, and then suddenly this goes to all the negatives. So you get negative z, negative x, negative y. So this is parity. These are the same thing. Well, turns out that these are the same thing. So if you're dealing with quantum mechanics and geometric algebra, when you compute the grade involution, you're actually just computing parity. So it turns out that so a general, also in GA, a general Lorentz transformation is capital lambda equals to b r. So thus, um, thus, if L, or capital lambda, this Lorentz transformation, if this is left-handed, or I'll do this, if it's left or right-handed, then, or I'll write it out like this, equals BR. If that's left or right-handed, then the grade involution, or the parity transformation of it, ends up being like this. The parity transformation, if you look at the grade involution, it doesn't affect bivectors. And since rotations have to do with bivectors, it doesn't affect rotations. And so when you when you perform a parity transformation or grade involution on the Lorentz transformation, you only affect the boost. which makes sense because that's what's being seen physically. Physically, these rotation matrices are the same for both left and right-handed vial spinners, but their boosts are different. And that makes sense because, at least in geometric algebra, when you perform grade involution, you only affect the boost component, which means that this is right or left-handed. Left-handed. So if this is left or right-handed, then this is right or left-handed. It swaps the handedness. So this is something that's not completely necessary for understanding the book, but I think it's neat. If you know geometric algebra, then you can see how geometrically the physics kind of falls out of the math, whereas here it's kind of stated ad hoc. Okay, and then we're in relativistic quantum mechanics. So in relativistic quantum mechanics, Dirac spinners are needed to keep track of both left and right-handed vial spinners. And here I will write a Dirac spinner. In this video series, I will write Dirac spinners as capital C. These are columns where you have the left-handed and the right-handed vial spinners. And both must be considered at the same time because left and right components are vial spinners. They swap under parity. So that means so now I'm going to write, even when we're not in geometric algebra, I'm going to denote parity transformations by superscript minus. So you have or specifically what it's saying is that under parity, left and right vial spinners will swap. And this can be expressed mathematically. If you have a left-handed Lorentz transformation matrix, then that will be equal to the right-handed matrix, but parity transformed. And then likewise, you have the right-handed, that's equal to the left-handed version, parity transformed. And moreover, if you have the Dirac spinner as equal to the left-handed and the right-handed components of the spinner, or vial spinners, then under a parity transform, then the spinners swap. And this is why they're needed to be described in they need to be described in as Dirac spinors because the left and right-handed components will interact with each other in a very specific way, and when you include them in column spinors, then they interact in exactly the way that's needed. Also, in geometric algebra, a four-column, or so if you're in 3D geometric algebra, like in here, it turns out that a Weyl spinor is an element of a minimal left ideal here of this algebra. But then 2 dimensions higher in the Dirac algebra, it turns out that Dirac spinors are elements of the minimal left ideal of the geometric Dirac algebra. And the geometric Dirac algebra just has 2 copies of spinors from the 3D geometric algebra. Okay, so hopefully that's enough information for you to understand spinors before we delve into the next video, which is spinor fields.